For the Data Science Clinic, we are the CMAP group, Spencer Ellis, Matthew Rubenstein, and Tamami Tamura. First, a brief project overview. Our project motivation, put simply, is mitigating the effects of climate change in the Chicago area. Climate change is accelerating at a rapid pace, leading to drastic landscape and weather changes. The Midwest is experiencing more extreme weather patterns than ever before, leading to increased risk of flooding, reduced water quality, and other environmental issues. These problems can cost local governments millions of dollars in damages and cause widespread destruction and harm to individuals' lives. In addition, as coastlines become more and more uninhabitable, migration towards the Midwest, magnifying already occurring urban sprawl, means that the areas surrounding the city of Chicago need to be prepared for habitation and further development of infrastructure. One key component of that preparation is ensuring that new developments don't flood after they are created, and that they have proper drainage systems for all of the water that humans use. To do that, however, Chicago needs to know how much stormwater drainage currently exists and where it is, so that they can calculate the effects of new development and create plans to build more drainage systems as Chicago continues to grow. That's where our partner, the Chicago Metropolitan Agency for Planning, or CMAP, comes in. They are a government organization tasked with watershed monitoring and future planning, but in terms of stormwater structures, they currently lack the data necessary to properly plot and plan for the future. Their intention with the creation of this project has been to create a method for efficiently identifying and mapping stormwater structures across northeastern Illinois, in an attempt to create a more thorough understanding of what needs to be done to improve or extend existing stormwater storage infrastructure. The term stormwater storage infrastructure refers to any type of outlet through which stormwater can be held or drained, such as wetlands, detention basins, and ponds, as well as more man-made structures such as permeable pavement, which lets rainwater seep through to the ground, unlike traditional pavements, or curbside bioswales, which generally are cultivated strips of land next to roads that allow for capture and filtration of stormwater. Part of the problem and identification of these systems, however, is the fact that no comprehensive inventory of stormwater storage exists across northeastern Illinois. For many types of stormwater storage structures, especially for the more natural systems such as wetlands, there's no centralized record of their creation, meaning there's no way to pool already existing datasets of stormwater storage system locations. And while the current Kane County dataset was collected by manually tagging individual stormwater storage infrastructure from aerial images, it's an extremely labor-intensive method of creating a stormwater storage inventory and isn't replicable on a larger scale. Our project goal, then, has been to automate the identification of stormwater structures throughout Chicago and the surrounding area, in order to create a more thorough dataset from which CMAP can plan for the future. An inventory could help county and municipal stormwater engineers, public works officials, and others to ensure proper maintenance, and could also inform the development of watershed-based plans and resilience plans. Ultimately, our deliverable can be used to increase climate readiness through more robust stormwater drainage systems across northeastern Illinois.
I'll be speaking about the model development work we completed this quarter. The available data came in different forms. Some datasets identified stormwater infrastructure with shapes, while others used points. Each piece of data had a label for the type of infrastructure it represented. The shape and point data served as the targets for the model to predict from the aerial imagery. The shape data was from the Kane County Water Resources Division, and the point data was from the Green Infrastructure Baseline Inventory developed by the Metropolitan Planning Council in collaboration with the Calumet Stormwater Collaborative. We used aerial images from the USDA's National Agricultural Imagery Program. We faced challenges when conducting our exploratory data analysis. Given that the data was engineered for ArcGIS, it was challenging to wrangle. We also had to manually test multiple coordinate systems to find the proper projection and had difficulty visualizing the data. We exclusively used shape data this quarter because it provided richer contextual information and allowed the model to identify characteristics of the infrastructure in the aerial images. We chose the four most prevalent types of infrastructure in the shape dataset. These were ponds, wetlands, dry-bottom turf detention basins, and dry-bottom prairie detention basins. These types of infrastructure were identifiable in the aerial images given the resolution we had. We chose to develop a segmentation model which would identify the classifications of infrastructure in a given image. Among deep learning models trained to interpret images, we thought that segmentation models were best suited for our needs. Segmentation models draw a shape around the object, as segmentation models categorize each pixel in an input image by class or labels. This is ideal because we have shape data that we can use to train the model to generate accurate results. With our segmentation model, the goal was to maximize the intersection over union, which is a measure of accuracy. The intersection over union measures the overlap between the model's predictions and the actual labeled areas. Once we had a basic segmentation model running, we began tuning the model to produce better results. By experimenting with different parameters such as the model architecture, the weights, image augmentations, and hyperparameters, we strive to get better accuracy. Model tuning was an iterative process, which required changing the parameters, running the model, checking the model performance, and repeating for different values and combinations of parameters. In early runs of the model tuning process, we had poor performance and little improvement. However, later runs saw greater improvement and much better performance.
I'll be going through some of the results of our model and then concluding the presentation. Looking at some of the model outputs, we can see that it does a good job of predicting the top two labels in our dataset, which are ponds and wetlands. High accuracy with ponds especially is achievable due to their well-defined shapes and significantly different features than the surrounding land. One issue with this, though, is that the model is simply good at predicting bodies of water, and so it doesn't distinguish between ponds and lakes or rivers. This has a negative impact on model performance and the IOU score, since the designation of some bodies of water as correct and others as incorrect with no perceptible difference in features confuses the model as it tries to improve. This is something that could be addressed with future work on the project. The accuracy with wetlands, on the other hand, is a promising sign since they can be very difficult to distinguish from just fields or other areas of wilderness. So the fact that the model can recognize them could indicate that with enough data, some of the other more subtle labels could be accurately identified. So this shows we have a strong proof of concept and that the use of our model to meet the goals of the project could be feasible. However, some of the labels have proven harder to predict, namely the dry bottom detention basins. As a quick explanation of what these are, they are areas of depressed land that act to capture and accumulate rainwater during times of heavy rain for temporary storage. So generally, at different times, these areas will have a completely different appearance on aerial imagery, since sometimes they'll resemble ponds and other times they'll resemble grassy areas. As a result, identification in aerial imagery that only captures one of these states may prevent the model from learning exactly what these areas are. Elevation data could also help to improve model performance, since the depression and elevation could be a marker of dry bottom detention basin. In fact, these additional data points are exactly what the experts who prepared the data set used for identification of these and other types of infrastructure, so matching the model input data to the workflow of the experts could yield a more accurate model. So this leads us directly to some next steps. First, more data is always preferable. The fact that some of our data was point data made it less useful to us for the model, since our segmentation model requires the additional context provided by shape data to classify pixels. Additionally, it was discovered that there was an issue with the projection of point data that we had, where the points were not aligning to the proper coordinates of the infrastructure it was identifying. So if it's possible to correct that projection issue and then convert that point data into shape data for training, that could potentially boost model performance. Also, as I mentioned previously, additional aerial imagery from different time periods can help with identifying infrastructure that has a significantly different appearance depending on environmental factors, and higher resolution imagery would allow the model to see smaller details. Elevation data could present similar benefits as well. Once the model is performing well on all the chosen labels, there's opportunity to extend it to other types of infrastructure. This would help to bring the model closer to being able to help compile a comprehensive data set. We're also in the early stages of exploring pre-trained models that are tailored to aerial imagery rather than general imagery, which is a task that could be picked up by users of our code down the line. A final important opportunity for future work is to implement a way to reduce the number of background-only images being used for training. With the current data, not all stormwater infrastructure is labeled, leading to instances where infrastructure is present but not marked, and therefore mistakenly identified as background. By curating the dataset to limit these mislabeled background images, the model would be less likely to develop a bias toward predicting background in the presence of actual, though unlabeled, stormwater infrastructure. To recap some of the major work we did over the quarter, as with any data science project, a huge part of it was understanding and analyzing the data to drive decisions on model development and what is actually possible. We then had to get the data in a form that we could use as input for a model, and then find aerial imagery that corresponded to the areas of coverage for our data sets before we could start actually building anything. When we did begin building a model, the challenging part was ensuring that it was dynamic enough to allow for different input hyperparameters to ensure that we could run multiple experiments to find an optimal tuning. With all this work, one of our biggest successes is that we've produced a strong proof of concept model that shows that computer vision can be used for the purpose of identifying these types of infrastructure. It lays the groundwork for future experiments, extensions of the model, which will hopefully move the project closer to its initial goals. Thank you for listening. This has been the CMAP group for the Data Science Clinic.